You'll have to ignore the slightly bunged up sound of my voice and the sniffling. I have a bit of a cold. Yeah, it wasn't really meant to be the keynote per se, but rather hopefully an enlightening talk on what we are aiming towards in terms of the developer API with our cross-chain message passing stuff. Point of note, it used to be called ICMP, interchain message passing, but there was a little bit of a name collision, so it has since been renamed. It's now cross-chain message passing. Cool. I'm not going to focus too much on the implementation of this. It's pretty complicated. There will be ample documentation on that if and when you want to look at it. But I'm going to focus mostly on the design and particularly like the sort of high-level API, and how it's built. So first, like the model that we're working with. We've called it, like, since the very start of the Polkadot project, it was called this kind of parachain thing. So, you know, it was really about like trying to get people to understand that the fundamental point of abstraction that Polkadot provides for people is one of like blockchain's runtime logic. So that's a little different to the point of abstraction for platforms like Ethereum, where it's really the smart contract. So it's small snippets of logic that can join a very large kind of environment. And talk to each other sort of synchronously. Parachains are different. They're much bigger. They're much sort of weightier, and they can talk to each other only asynchronously. Nonetheless, it's important to understand the difference between what we wanted to achieve with the name Parachains and blockchains in general, and in particular the difference between the bridge model and the sort of shared security model. The bridge model is one where each individual chain looks after its own security. Messages can be passed between them, but the messages are largely meaningless unless you trust the security apparatus, the validator apparatus, the amount of stake behind those validators, so the economic guarantees provided to you by them of where the message is coming from. If you don't trust that, then the message may as well be garbage. And therefore, bridge-based solutions are fundamentally trust-bound. Now, when an Ethereum contract talks to another Ethereum smart contract, it's not trust-bound, right? It's trust-free, it's trustless. Because the same validation logic that talks to one, that defines the transition of one smart contract defines the transition of the other, right? It's the same economic guarantees that you get for one being correct as for the other being correct. And indeed, for the synchronous call to be passed and executed faithfully. So everything is guaranteed by the same underlying security umbrella, and that's why it's useful, that's why it's good. Polkadot provides that very same guarantee to all of its underlying parachains. So in many respects, it's more sensible, it's more poignant to call it a sharded solution, because the parachains are all sort of executing in parallel. In that regard, it's like a heterogeneous sharded solution. And probably going forward, to try and remind people of this, we will be using more the sort of terminology of sharding than the terminology of multiple chains, because ultimately it's a really fundamental difference in how these systems operate. The final point is the important one: deterministic message passing. So basically, you get certain guarantees about when you send a message from one parachain, when it will arrive and what it will do potentially in another parachain. But in particular, the messages will arrive exactly once and in order compared with each other. And yeah, there'll be a sort of definite period of time that it takes, although it could take very long depending on how often the destination parachain or parathread is scheduled. So there are three directions that messages can go within the Polkadot model. And therefore, for any parachain built with Substrate, there are sort of three kind of APIs that you need to know: up, down, and the more interesting one, sideways. So up is relatively easy. There's like order n possible endpoint combinations. Basically, it's just all of the different parachains. They can each send a message up to the relay chain. Same with down. If the relay chain ever wants to send a message to a parachain, it's not too difficult to arrange. Now, these are already in the current sort of Polkadot code base. These are already implemented. The hard one is the lateral one, right? Because suddenly you've got all of these possible different endpoint combinations. Now, in the original Polkadot model, where it was all just parachains and all the parachains were always scheduled all the time, n here was maybe 100. But in the new Polkadot model, where we have parathreads as well, yeah, and parathreads take sort of share part of the scheduling space, the n has sort of grown quite a lot. Now it's like maybe 10,000. So that's really quite a lot of endpoint combinations. So yeah, talk a little bit more about this, the Parathread model. I don't know how many people are super familiar with it, but basically the idea is that you've got a bunch of different parachains that can be scheduled each block. Let's say maybe there's space for 100 different parachains. This is, there's a few factors that lead to this upper limit. One of the factors is just the sheer number of validators. So maybe you've got 1,000 validators and you want 10 validators that are scheduled to validate a single parachain. Then that limits you to 100 parachains. Now, if you can scale it up to 10,000 validators, maybe you can now get 1,000 parachains per block. One or two of the other things, like maybe availability, so guaranteeing that the data that all the parachains need to be around as they sort of continue onwards, it may be difficult to arrange for all of that data to be continuously available. So there are one or two kind of things that do limit this amount, but potentially it could go higher than 100. We'll just have to see. Now, parachains, there are sort of two notions, two rough sort of families of parachains that we're going to see. We'll see leased parachain slots and also kind of permanent parachain slots as well. These are the things that just sort of get deployed and they stick around in their slot every block for some long period of time, maybe 6 months, maybe 2 years, maybe indefinitely, we don't know. But as you can see in this lovely little diagram I did, pink, purple, and blue are a sort of leased parachain, and they just hog their slot. They stick in their slot, and they just continue getting scheduled in their slot as time goes on. Now, parathreads are scheduled dynamically, so they're the things that can be swapped in and out. And there's a few different colors of parathreads, the pastels there at the bottom, and they're getting, as you can see, scheduled dynamically once in every block. Realistically, I think these are not crazy numbers to aim for. So maybe 50 leased and permanent parachains, and maybe 50 that are just sort of parathreads being swapped in and out every block. And as I said, up to 10,000 on version 1. So 100 million possible endpoint combinations. Actually, it's 200 million because you've got both directions. Yeah. So A can send to B, but also B can send back to A. So yeah, if we look at the requirements for XCMP, they're fairly harsh. 10,000 endpoints. Maybe 100 of those are going to be sending or receiving in any given block. We need hard delivery guarantees. And also we've got this irregular servicing, so it's like different, some threads may be serviced only once a day, and then what do you do? Like, if everything else is sending to it, you've got to make sure that the queue doesn't just build up endlessly. Oh no. So XCMP has a bunch of important sort of design decisions. Firstly, it's connection oriented, which means you can't just go spamming messages to like 10,000 different chains. Yeah, you have to choose which chains you're going to want to talk to, and you have to. There's economic impetus to keep this relatively low. One of the pieces of economic incentive is by placing a deposit down. So you have to put a deposit down in order to actually make a connection. You get the deposit back once you've closed it, but it will cost you basically. Crucially, the relay chain is not used. It's not a point of throughput for these messages. It's not even a point of throughput for hashes of the messages. It's not even a point of throughput for like chains of heads of chains of hashes of messages. It's substantially indirectly linked to any of this messaging. It's only used basically to check whether, or to provide a top level proof, a top level Merkle root in order to provide eventually proofs to the parachains that a message was posted at some previous time, or that essentially it must have been received at some previous, or delivered at some previous time. So it's used really just to record very, very, very indirect high-level information, and it's not the sort of thing that's going to sort of cause it to become a bottleneck for the sorts of numbers that we're talking about. And as I said, proofs are used based upon this information that's stored on the relay chain in order to push all the work that needs to be done out to the edges, out to the parachains, and particularly makes collators' lives quite difficult in order to do this, because they have to sort of go off to various different points in the system, collect lots of information, and create these proofs in order to prove to their own validators, and particularly the relay chain validators, that when they're delivering messages, that these messages were indeed sent. So yeah, the channels in XCMP, so this connection-oriented design, each channel is, firstly, it's like simplex, so it's just unidirectional. There's a from and a to. The to can't send back to the from. And it's here in order to bound the total endpoint combinations to well below 100 million. The other point of doing channels, of doing this connection-oriented design, is that the receiver needs to have control over who can send the messages. Very important. So broadly speaking, let's go into the stack. We've got a sort of four layers of kind of API. At the bottom is the thing that's the only real sort of proper thing that's done on chain. And that's the relay chain messaging. So that's the ability for Parachains to send messages up to the relay chain. And there's, as I say, there's already a sort of API in place to do that. There's also a sort of means of getting information from the relay chain down into the parachain. It's basically just done with inherent data. If you're familiar with that, you probably have heard of it if you've been here for the full conference. And it's checked by the relay chain validators, or the parachain validators that also happen to be the relay chain validators. Built on top of this are the basic sort of XCMP building blocks. So the APIs that you're able to use by conversing up to the relay chain. And then built on top of that is the sort of end user, that would be kind of you guys, queued XCMP, the lower level of the two sort of end user APIs. And then there's also dispatched XCMP, which I'll talk briefly about, which is the sort of do nothing, super easy variant that is quite opinionated and but may well be useful for some people. Yeah, so as I say, the thing at the bottom is the foundation of all of this stuff, so it's worth sort of understanding what is provided. Essentially, it provides this message path from the parachain back up to the relay chain. So you've got this post message thing. I need to change this. So that dest para ID shouldn't be there. It's really just post message, data, and then the data will arrive at the relay chain. Actually, the data, although it's just an opaque blob, you know how to encode it because it just needs to be a call that the relay chain can interpret and enact. So you're familiar with like calls or proposals, these kind of serializable function objects that can get dispatched via the runtime. That's just one of those, but it's encoded. And similarly, you can get these blobs of messages back out. There'll be an API for that. At the moment, it's really just inherent data that you have to read directly, but we'll put an API in for that in the not too distant future. The messages that you send to the relay chain go into a FIFO. The FIFO is serviced, and yeah, it's that simple, really. There's super strict capacity limits. Basically, it's quite low. You can sort of send up to, I don't know, something like 16 messages per block. And you can only send up to, I don't know, like a megabyte or something of data. So it's, yeah, it's pretty small. Yeah, I've gone over this really. So the parachain has to figure out how to talk to the relay chain, but as I said, the relay chain essentially isn't going to change, so it's not too difficult to figure that out. So given that we've got this like base conduit to go up and down to the relay chain, how do we sort of, how are we going to build on that to make XCMP? Now this is really the job of Cumulus and parts of the bits of the relay chain, sort of part of the bit of the Polkadot client code and some of the runtime code. That's where this logic sits primarily, and it's this logic with which we will build the real user API. So the first thing is channel setup. There's an API for this, and it's done in terms of basically just relay chain, a relay chain runtime module, right? Relay chain palette. There'll be a dot deposit to set it up. We're going to assume for now that the messages are coming from Parachain origins. Yeah, so there's already part of the thing that we delivered with the relay chain messaging there. Is this notion of being able to send or have a message, have a call be enacted on the relay chain from a particular origin. The origin, you can choose whether it's an account origin, account ID, one specific to your parachain, or a special parachain origin. And these will probably work with the special parachain origin. Okay, so there's, as I say, there's a bunch of kind of TCP/IP looking functions that you can call on the relay chain from a parachain. Connect, accept. There's the interesting one is accept because it's got this max pending count. Max pending count is basically the queue size. It's how many messages, or specifically batched messages, so kind of blocks worth of messages, that can be not yet delivered before the channel becomes full. This is sort of to mitigate the possibility of a channel, sort of a particular chain being spammed just by, it being sent tons and tons of messages, and it would be very difficult for it to get through them potentially to some important messages that came a bit later. So where were we? Yeah, they would require dot deposits. So for these to be called on the relay chain effectively, you'd have to, the parachain itself would have to have dots within its account, or Kusamas if it's on Kusama. Yeah, I think that's probably it. So the connect and accept is like one, the sender would attempt to connect, and then at some point later, the receiver would check to see what the incoming things are, and if it's got any incoming things, it would see if it wants to accept messages from them, and if it does, then it would accept that para ID, and it could also sort of disconnect or whatever from the para ID if it didn't want to. Now, we get onto some of the more kind of interesting elements. So actual message passing. So within, for any given channel, at most one, at this abstraction layer, one message may be sent per block. at this abstraction layer. Now, at the next abstraction layer, you can send many messages per block. So I've decided to call it this abstraction layer, they're just called batches of messages, or message batch, right? So one batched message may be posted per block. And you can think of it literally as that, just all of the messages that this particular parachain is sending into this channel at this block are just going to get glued together into a big vec, and that's and it's all serialized anyway, so it's just going to be a big opaque blob, and we call that the message at this point, but actually it's the batch of all these messages. Now, at most one can be posted out. I say posted rather than sent because I just want to get across the fact that it's asynchronous. It's like really asynchronous. And we also may have some that are already pending delivery. They're still waiting to be delivered. If there are, then it would limit the amount that can be sent, potentially down from 1 to none. The API is relatively simple, but as I say, you can only send at most one message per block. So rather than it being a kind of post message API, it's really just a set message. So if you don't want to send any messages, then don't call it. And if you do, then you call it exactly once. And it's just where the message is meant to be posted to, and this batch of messages, which is actually just a big opaque blob. And if there are too many pending messages, then you're going to get an error back. Or for that matter, if the destination, if there's no channel open to that destination. Now, in terms of getting messages in, at this abstraction level, it will be a push model. So messages are going to come in when they come in, and it's up to you, the Substrate parachain, to know what to do with them, to handle the fact that messages are coming in. At this one, it's going to be just basically a function that you call to see if there's, you call it once a block to see what messages are coming in this block. If you don't call it for whatever reason, then the messages are just going to get ignored. As far as the system is concerned, they've been delivered, and it's up to you to make sure you actually service it. At the back end, it's actually just an inherent data. So it's coming in from the relay chain. It's going to deliver these messages into your parachain. Your parachain is going to be checked to make sure it's delivering the right messages. And you end up with this kind of, this vector of this bunch of messages coming from various places, various para IDs, various parachains. And you also get the block number that they were sent out. Presumably, you're not going to always be able to act on all of these messages immediately, and therefore you're going to want to have code that like buffers and potentially persistently, and also enacts them, like does some action based upon their contents at some point. Now that's going to be handled in the next two things, but at this sort of quite low level layer, that's what needs to be done. So, right, now we're to the top two bits of API. These are the bits that people will actually use. So if you're interested in talking to other parachains from your substrate chain, this is the important bit. Now is the time to wake up. Okay. So the first point to make about queued cross-chain message passing is that there isn't a data format. We're talking about sending blobs of data between parachains or parathreads. Entirely arbitrary. So it's up to us, the Polkadot community, to work out what these formats should be. Now, as you'll see in the dispatched XCMP, there's one suggestion for what the message format could be. But at this point, it could be anything. Like at this layer in the stack, it could be anything. And it could be different depending on what the channel is. So it might be that you've got a channel between parachain A and B, and they're expecting, message format foo, and in the parachain, in the channel that's connecting A and C, they're expecting some entirely different message format bar. It's entirely up to the parachains or parathreads in question to work out what language they're going to use to talk to each other. But I do expect there to become message formats fairly quickly, and I do expect, I think it's at least possible that we will see message formats even starting to sort of work outside of the purely Polkadot ecosystem. We might see some other cross-chain standards arising, but we'll see. So what will it look like? Well, the first thing is that channels will be handled a little bit more. So this is, just to give you some idea of where this code sits, this particular code will be in the Cumulus code base. It will be, there'll be a couple of palettes probably that you can sort of bring in order to, kind of XCMP palettes in order to be able to send messages. So there's one of the things that will be in these, one of the pieces of logic in these palettes will be this channel tracking logic. So you've got, we had the sort of TCP/IP style API from before that sat on the relay chain. Well, in addition to that, there will be this kind of slightly nicer API that will essentially prevent the possibility of you accidentally sending to a para ID that isn't actually a channel. So you've got this lovely kind of try-from interface to turn a para ID into a channel. So you can get a channel value from a para ID value or get an error. And then once you have this channel value, then you're guaranteed you can definitely send to it. The channels is also something that you can call in order to get all the channels that you currently have open. So you can also just, if you want to do a multicast, you can just send to all of them just by iterating on this vector. There's this post message API, so it gets given a channel and you also put a message in. And the idea is that it's infallible. So all of the checking that's done to make sure you can send a message, to post a message, is already done as part of the creation of these types or creating values of these types. Once you have the values of these types, then you're guaranteed to be able to send. Message would be, you know, a try into from, oh no. Do we have power? Okay, I have power. For some reason, I think my machine's compiling something. I'm not really sure what. Okay. Yeah, so the idea is you can give it this sort of blob, this vec of U8, and as long as it's the right size, then it'll give you this message back. But the messages, as I said, are still very much opaque. It's up to the parachains, up to the sort of the code and the parachain to work out what format these messages are in. In terms of receiving messages, we've now moved from a push model to a pull model. Basically, all that means is that the code inside this palette that you're going to be using will look after all of the sort of pain in the ass buffering and queuing and all that sort of stuff. All you need to do is you get this, like, maybe an iterator, maybe just the function next message, but you call this next message and it gives you the message, right? Or none if there's no messages to get that need to be serviced. And then it's like basically up to the parachain, Parathread, in order to make sure that next message is called enough just to keep the thing moving. In principle, you know, some of these things are going to require action. You know, they'll require some form of some logic to be conducted. Maybe it's like a, I don't know, transfer fund message, in which case you're going to have to like access storage, reduce a balance or add a balance or whatever it is. So it's up to the chain to work out how much work is being done and make sure that the work that's being done in servicing the messages isn't going to lead it to creating like oversized blocks. So that's part of the responsibilities at this level. But at least you're guaranteed that all of the messages will be queued and they'll be ready waiting for you in this like next message call. You don't have to worry about sort of having to service inherent data or anything like that. And you also get, as part of the delivered message, you get when it was delivered. So you can work out, I don't know, it might be useful to you. You can work out on the chain how long it took from when it was sent to when it arrived. At this level, messages, as I mentioned, are smaller. They're like the individual things that you would most likely call messages rather than these things that are all glued together such that you can only have one of them per block. So it looks after all of the splitting them up and gluing them together at this point in the API. Okay, so that's the main sort of cross-chain message passing XCMP API. That's how it looks. There's a sort of layer on top, dispatched XCMP. This is, I just want to give you sort of a vague idea about the sort of thing that I sort of might be doing in order to, or we might be doing in order to make it a bit easier. With this API, the channels remain the same, but the main thing is that the message format is fixed. It's fixed according to what basically looks like an unsigned transaction. So you're familiar with how transactions are encoded. You've got these like calls, right? These kind of function objects that can be serialized. And there's an idea that when you execute them, you're going to sort of add to the current weight tally of the block. So this prevents you from creating oversized blocks that take forever to execute, a little bit like gas. It basically handles all of that. It does all of that stuff. It also does fees, and it does everything. So it's very, very similar to transactions. The only difference is that rather than being signed and being floating around in a transaction queue and eventually heaved into a block, they come from other parachains, and their origin is guaranteed by the relay chain validators, not by any particular signature. So in terms of receiving these things, it's already done, because you can already receive transactions, yeah? There's all the apparatus, all the logic there in your Substrate chain to process transactions and manage things like weights and do stuff like fee deduction. So actually it's sorted, like it will just piggyback on that. Sending is a bit harder, right? Because there's no logic on the chain at the moment that creates, well, there is actually, but it's a little different, that creates transactions. The logic that is on the chain that does this works because it knows the chain that's creating the transactions, or the sort of environment in which the transactions are being created, is the same environment that they're going to be interpreted. It's the off-chain worker stuff, if you're not familiar with it. But in XCMP, they're different, right? The chain that's creating these transactions, the chain that's sending or posting these messages, is going to be different to the one that's interpreting it. It's going to have different modules. They're going to be sort of composed in different ways, parameterized in different ways. So there needs to be some way that you can you can sort of encode what it is that you want to do, encode your message, encode your instruction, your sort of transaction-like thing, from one chain, and sort of make sure that it gets is comprehensible and is going to do the right thing in the destination chain. And it's not particularly easy, but roughly speaking, it will probably look a little bit like this, where you're going to use some palette that you know that the destination chain is using, or is going to be composed with. Then you just create some sort of call using the palette's call enum, encode it, and then there's got to be some addressing, right? That's what this sort of balances thing is. You need to know what the palette, how it's instantiated, and what the name of the instantiation will be, so that it can eventually get dispatched properly on the other side. And that's the difficult bit. It's also a little bit stringly typed, but you know, hey ho, there's not much that you can do about that at this stage. Cool. That's the end of the talk. I hope you go away a little bit more enlightened than when you came in. And I think now, in case you're not, you can ask questions. Cool. Thanks.